interested in joining. For anyone that's interested in joining any of the IPPSA committees, reach out to us and let us know. But with that, we're a few minutes in, so we'll get started. Like I mentioned, today's session is about occupancy. We like to make this a little bit more informal, as we mentioned. It's the IPPSA mixes, so try to rhyme. And this one's where are your people at? One size occupancy scheduling does not fit all, and it's really meant to speak to a few different aspects of occupancy within the building. We have 3 different speakers today discussing different aspects of these that may be interconnected. I think one of the presentations definitely leads into the other. And yeah, we'll leave room for questions in between and also at the end. So with that, we'll get started in the first presentation. Oh yeah, and as ibpsa-usa noted, this is an AIA credit. There is AIA credit available for this MIXA, so reach out if you need that. Our first speaker will be Yeonjin Bae. She is an R&D staff in the Grid Interactive Controls Group in the Electrification and Energy Infrastructure Division at ORNL. She has a PhD in civil engineering from Purdue and joined ORNL in 2019 and currently is involved in various DOE-funded projects regarding building energy modeling and validation based on the extensive background for simulation and modeling and energy efficient building system optimization. She's the sub-program manager at ORNL for the Tech to Market program, a part of the Building Technologies program. And she's an active member of ibpsa-usa and ASHRAE, and a voting member of ASHRAE TC 7.6, Building Energy Performance. So we're excited to have her presentation. So I'm going to hand it over to you for our first one.
Thank you for the introduction, Nicola. I'm so happy to introduce one of my previous projects that perfectly matches with our topic today. So let me share my screen. Okay. Can you see on my screen?
Yes, we can.
Okay. So let me start my presentations. So traditional energy models often rely on generalized occupancy assumptions that don't always reflect how buildings are actually used today. So one of the example is the Open Studio prototype model for college buildings, and it applies standard school and office schedules and uses occupancy density based on ASHRAE 60.1. These are great for consistency and broad applicability, but they don't necessarily match the way a specific building is being used on a daily basis. The challenge is that this kind of data is highly building specific, and it's difficult to generalize across different institutions or campuses. But when we are focusing on a particular building or project, using actual data can significantly improve the accuracy of our simulation and better reflect real-world operations. So if generic schedules don't fully reflect how college buildings operate and the actual data is hard to generalize, then the question becomes what method can we use to generate more realistic occupancy schedules for college buildings? And beyond that, even if we have real occupancy data, how can we generalize that to create representative schedules that work for typical college buildings across different campuses or regions for the Open Studio prototype model? So we've taken a closer look at how college buildings differ from other buildings types, such as K-12 schools and offices. And unlike primary or secondary schools, college buildings are often discipline specific, and you'll find spaces dedicated to teaching, research labs, student work areas, and a wide range of auxiliary space that support various academic activities. And another unique characteristic is the variation in the type and size of classroom. And this largely depends on the number of students enrolled in different courses. As a result, college buildings tend to have many different space types, each with its own occupancy pattern. In some ways, this is similar to office buildings where occupancy behavior is influenced by schedules and individual use, but in colleges, it's even more complex. Most importantly, occupancy schedule in college buildings are linked to class schedules, which can vary by day, by semester, and by discipline. So our team developed realistic occupancy schedules. In order to do that, we started by collecting the actual operating schedule for different spaces types in college buildings. And this includes data on when classroom, labs, and other spaces were actually reserved for use. And based on these schedules and by applying appropriate occupancy density values for each space type, we were able to estimate the actual number of occupants over time. And the class reservation schedules we collected were from 10 randomly selected US universities that publicly share their schedule informations on their websites. And you can see the distribution of those schools across the map here. And here's how we collected and processed the data to generate realistic occupancy schedules. And first, we gathered classroom reservation data, either through their official website or through direct contact. And we focus on 4 major space types: classrooms, laboratories, art classrooms, and lecture halls. And as you can see here, we collected 605 classroom reservation schedules and 61 laboratory reservation schedules and 28 art classroom reservation schedules and 7 lecture hall reservation schedules. Once we had this data, we organized the schedules per university, then created average schedules for each space type across all 10 schools. And this allowed us to build generalized but data-driven occupancy schedule for each type of space. On the right side, we have listed some of the key assumptions we've made. We used the fall semester to represent a typical academic schedule. And the summer schedule was defined from June 1st to August 31st. And we focus on Monday through Friday, assuming no occupancy on weekends due to reservation schedules not available on weekends. And finally, all occupancy schedule are based on average classroom reservation pattern collected from the selected 10 universities. So this slide shows the box plots of the occupant schedules as percentage for the classroom, laboratory, art classroom, and lecture hall during the semester. And the boxes in these figures indicate the first and third quartiles, and the horizontal line and X symbols indicate the median and mean values of registration schedule. As you can see here, hourly schedule of the classroom and art classroom and lecture hall show significant variation during the occupied hours, which means the use of room is notably different in each space for each university. And here you can see the box plots for the summer vacation period compared to the previous the semester schedules. In general, spaces that support teaching activities show a significant drop in occupancy and during the summer compared to the typical operation hours in the regular semester. So based on all of this data, we generate the occupancy schedule and compare the updated schedule with the previous ones, including the semester schedule and the summer vacation schedule. As you can see, there are significant difference between the updated and previous schedules, especially for classroom, labs, and art studios. And these spaces are not continuously used throughout the day. and occupancy tend to be dropped sharply during lunch and dinner hours, like the office buildings. And during the semester, the updated classroom schedule shows that fewer than around 50% of the classroom are occupied at any given time. This is because college class don't all run at the same time, unlike K-12 schools where schedules are more uniform. And in the summer session, usage drops even more. For example, classrooms on the left side, on the top, only about around 15 to 20% occupied between 8 a.m. to 2 p.m. and just like below 5% from 3 to 8 p.m. And also one interesting case is the lecture hall on the right side bottom. The previous schedule showed a large occupancy peak in the evening, but the updated data shows 0% occupancy after 5 p.m., meaning that no evening class were held in the sampled lecture halls during the summer. So in overall, this comparison highlights the importance of using real class reservation data, especially to distinguish between regular semester use and summer sessions. As mentioned earlier, the occupancy density in Open Studio prototype models, including college buildings, was defined based on ASHRAE Standard 62.1. And on the left side in this table, you can see the occupancy density values per space type. And classroom and lecture hall have the highest density, around 699 people per 1,000 square meters, whilst space like offices or lounges have much lower densities. On the right side, you can see the differences of occupancy schedules. Previously, only 3 occupancy schedules covered the whole prototype college building model, and only 1 schedule covered all teaching space. But in our updated model, based on our collected data, we used 7 occupancy schedules, including updated occupancy schedule of the classroom, laboratory, art classroom, and lecture hall. And this allows us to better reflect the distinct usage pattern of each space based on actual reservation data, instead of assuming that all instructional areas operate the same way. And this slide shows that our comparison of average number of people in each space type based on the updated versus previous occupancy schedules. As shown on the left side, we see a significant decrease in average occupancy after applying the updated schedules. For example, laboratories decrease around 65%, and art classroom, and lecture hall decrease by 40 to 50%. And these reductions vary by space type and reflecting more realistic usage patterns captured from actual reservation data. Because the number of occupants has decreased, the required mechanical ventilation rate also dropped, shown on the right side. In particular, lecture hall saw the largest changes, with the ventilation rates decreased by about 25% to 32%, depending on the version of ASHRAE 90.1. And these results suggest that using updated occupancy schedules can lead to more accurate energy modeling. To wrap up, the main goal of this study was to develop a more accurate occupancy schedule for Open Studio prototype college building based on actual space reservation data collected from US universities. And our research results show that using a generic schedule like those from a commercial or school building models tends to oversimplify how space is actually used in colleges. And this can limit the accuracy of simulation or energy modeling. So as a next step, we plan to expand the data set by collecting more class reservation information from a broader range of universities across the US. And of course, this work was developed specifically for the Open Studio prototype model, so the current scope is somewhat limited, and further studies will be needed to generalize the findings across different modeling framework or building types. And thank you very much for your attention. So here is my contact information. If you have any questions, feel free to reach out to me or ask questions today. Thank you.
Thank you so much. We do have a few minutes reserved for questions at the end of each presentation, but we also know that some people might have like a joint question that is related to all presentations. So just want to leave it open. Does anyone have any thoughts or questions?
Hi, I have a question.
Hi, Sunny.
Hi. Thanks for the great presentation. This is great information as we work with a lot of universities and do a lot of energy modeling for these type of buildings. So this is great. And I'm wondering, could you expand a little bit more how you collect the data? And do you think it's replicable for or feasible to do it for every project versus it would be too much?
Okay, so first of all, not all of universities shares their class reservations on the website, but most of the big schools like State University post their reservation schedules by yearly basis, so you can access easily and on those informations. And also some of the if you reach out to the department level admins, then sometimes they are ready to share all those information for the research. So we've got like 80% is directly gathered from the website resources, and 20% is from our the private contacts. Yeah.
Thank you.
Great, thanks. Yeah, Sunny and I together didn't plan that. So thanks.
If
Any other
you,
questions?
yeah, I have a quick question. Like, are there specific building types you have in mind that you, if you could go expand this beyond universities or education to other building types that would be high on your list?
Beyond the college buildings. So yes, some special buildings like the hospitals or library, those are difficult to get the even generic schedules. So if we can utilize publicly available resources, I think we can come up with real representative schedules for any building types. But as you know, the offices or all of typical commercial buildings are easily accessible, but some of the small, not a typical building types like library, those kinds are difficult to get. So, but at the same time, those based on our preliminary research, we found out that some of the data is publicly available, and we can definitely utilize those information to make to come up with a new set of occupancy schedules.
Thanks.
Thank you.
I have a question.
Yes.
Hi. Thank you for the presentation. I'm a graduate student at Texas A&M, and I wanted to ask you have you ever considered in analyzing resident halls at the university? Because I see a lot of lecture rooms in your data set, but have you ever considered the resident hall itself?
So it was difficult for us to gather those information. So only class reservations, and those class reservations are limited to typical classes. So that's why we the data that we collected for lecture hall, those kind of things are very difficult to get on the website. So I would say, yeah, resident hall might be a little bit difficult for us to get the information on the website. But if we can get if we have a chance to get those information, it would be great for us to come up with some other building types just for the campuses. Yeah.
you.
Great. Any other last questions before we switch presenters? Again, there will be time at the end as well, so all of our presenters will stay on. Okay,
Thank you.
all right. Thank you so much, Yeonjin. Appreciate it. On to our second presentation today. Jeetika, are you ready with your screen? Maybe if you share your screen and then I'll do your bio.
Sure.
Yeah. Great. Okay, so our second presenter is Jeetika Malik. She's a research scientist with the Building Technology and Urban Systems Division of Lawrence Berkeley National Lab. Her research efforts are directed towards improving thermal and grid resilience within buildings, evaluating building technologies for effective policy making and housing affordability, and exploring human factors related to building design and operations. She holds a PhD from IIT Bombay, India, and actively contributes to IEA-EBC Annexes, ASHRAE technical committees, and other professional societies for research bridges technical modeling with real-world decision support for utilities, cities, and resilience planning. I'm excited to have you, and I'll hand it over to you.
Thanks, Nicole. Hi, everyone. I'm Jeetika Malik, and today I'll be presenting some of our research here at Berkeley Lab, focusing on occupant modeling, specifically occupancy, and different tools that we could use for modeling occupancy, and then also a novel concept of level of detail that is related to how we can model different levels of granularity in building performance simulation, and how should we decide upon what level of detail modeling should we be doing for each of our use case or building models. So why does occupancy matter? All of us know that occupants play an active role in building energy demand. It could be related to how occupants interact within the building. It could also relate to how they operate different appliances, or even simply their presence. And to ensure that we have accurate occupancy would lead to improved estimation of energy demand. Other than that, we also have, most of us know that occupancy also relates to space utilization, how to be optimized building layouts, room configurations, and then there is a new, there has been for the past few years, there has been a good line of research on occupant-centric controls, particularly HVAC controls, lighting controls, and then having the detailed or accurate information about occupancy could also help us improve building design operations and ensuring that these lighting or HVAC controls are used efficiently. And lastly, this might not relate to the IBPSA community, but for the broader audience, occupancy also matters in case we are looking at evacuation planning, emergency planning, or even, say, resilience planning for heat or other hazards. If we know what kind of occupancy, what density do we have in our buildings, we can plan accordingly. Next, I'll come to what are the different approaches to model occupancy. We know there are several ways how we input model occupant information, occupant presence into our building energy models. The simplest and the straightforward way is using a fixed average occupancy. Say we assume that there are 3 people in a household and they are present 24/7 in a home. This is the simplest that we can do. However, with each different use case and each different objective, we would need different kind of occupancy modeling approaches. The second one is more schedule-based, that the previous presenter was mentioning, which is more like there are occupant schedules for daily, weekly, and the patterns are predictable, and it's more of deterministic. It could be hourly, 15 minutes, and so on. And then the next level is stochastic, which is probabilistic, where we have some variability within the occupant presence, and it's based on statistical distribution, generally Markov chain models or random variability. And lastly, which is a higher level of detail, is an agent-based or a dynamic probabilistic modeling, which is basically we model each and every occupant. Each occupant is assumed as an agent, and then they dynamically respond to different environmental and other agents around them. And this is more like a real-time or adaptive occupancy. And though this kind of modeling needs a lot of data, but then these days there is synthetic modeling, there is big data, we have machine learning approaches and plenty of other approaches where we can use or integrate those approaches to develop these agent-based or probabilistic models. So once we have those models, how do these different modeling approaches, how do these actually matter within our building energy modeling simulations? So here is a quick example of how deterministic versus stochastic occupant schedules within an office building impact the efficacy of different energy conservation measures. We actually developed these, we used a DOE prototype office model, and then for this baseline, we used a fixed occupancy. Then for the second one, integration, we used a stochastic occupant schedule for offices. And then for the third one, we just simply used the DOE prototype model schedule. And then when we simulated these different occupancy approaches and applied some energy conservation measures to this baseline model, we found that just because we were using these different type of occupancy assumptions, with the overall occupancy being still the same, there were significant differences in the energy saving potential of different measures. This is for the case of Chicago, but overall we tried to estimate it for 5 different climate zones, and we were able to find that stochastic schedules were able to get the potential of energy conservation measures in range of 25 to 41%. However, deterministic schedules like the DOE prototype model schedule is able to get this range to 9 to 23%. So keeping everything the same, just changing how we input occupancy can have a huge impact on the energy saving potential of energy conservation measures. So it's definitely important to understand and to make a judgment about how do we want to model the occupancy within our particular use case. So now I come to this concept of level of detail. This level of detail concept is very similar to what we already have in the building information modeling industry or in the urban scale city GML approaches of level of detail. However, here, what we're trying to achieve is we are here trying to say that the level of detail, the concept, is broadly applicable for occupant modeling. And then occupancy is a part of it, which I'll come to in the next slide. And level of detail is essentially the degree of detail or the granularity that is used to represent complex human behavior. And then human behavior would have elements such as occupant presence and movement, their interactions, how do they negotiate, or even simply how do they make judgments or decision making. So there are plenty of behavioral aspects that this level of detail concept entails. And then what we say here is that this level of detail is an important concept and framework to help us assess at what level should we be modeling occupants. So for occupancy related level of detail, we could have 3 different dimensions. The first one is modeling formalism, which I mentioned in the previous slide. The second one is at what spatial scale? Is it zone level or building level or city scale? And then the temporal scale. At what temporal scale do we want to input this occupancy? And all these dimensions would actually depend on certain use case parameters. For example, there are different building design phases that we are using for our particular use case. There could be different spatial scales and the model objective. For example, if we are using an occupant comfort analysis at a detailed design stage at a building level, we would definitely not want to model a static average occupant in a building, given that our focus is on occupant comfort and not maybe compliance, code compliance. So I'll come to all these details and nuances in a bit, but before that, I'll introduce this level of detail framework for broader occupant modeling. This framework we developed as a part of Annex 79 International Energy Agency's project, where over hundreds of researchers came together to understand how different occupant modeling approaches, case studies, techniques can be improved. And this was a part of that project. Here we have 10 different aspects of occupant modeling. The first 5 are related to the model structure, and occupancy is one of them. And then the next 5 are more related to behavior, like how do occupants sense, predict, learn, and others. And all these different tiles are actually different level of detail that we could go into for modeling each of the occupant aspect. For the occupancy, these tiles are very similar to what I presented earlier, the static, deterministic, probabilistic, and the agent-based dynamic probabilistic approaches. And here we say that the static is considered LOD0, while the most granular is considered LOD3, the agent-based model. And how do we decide upon this? It's basically related to these 4 characteristics on what are we trying to achieve in our model, through what performance indicators, at what spatial scale, and what is the building type that we are considering. For example, if our objective is simply an early design stage analysis, maybe a lower level LOD would be good for comparison. However, if we are having this detailed occupant impact analysis, we should have some medium level O2 or O3 kind of analysis. And these levels of detail are only indicative, and they are not comprehensive enough. We could have level O1 to O9, depending on what kind of granularity and what kind of combinations do we want for the different occupancy dimensions related to spatial scale or modeling formalism or the temporal scale. Then for the performance indicators, again, if we are looking at high level performance indicators like annual energy use or energy star score, maybe a Courser LOD would be feasible. While if we are looking at detailed occupant level performance indicators, we would want to have occupancy that reflects or can connect to those performance indicators like partial occupancy criteria or occupant hour criteria. Similarly, for spatial scale, if we are looking at, say, zone level HVAC controls or lighting controls, we would definitely want the occupancy to match at that spatial level instead of modeling occupancy at a building level while doing the analysis at the zone level. And lastly, the building typology also plays a great role, given that different buildings have different flavors of occupancy. And say for retail buildings or restaurants or schools, which are more homogeneous, I would say, it still makes sense to have LOD1. However, for specialized environments like hospitals or even transient environments like airports, we would definitely need a higher level of detail to make sure that we are modeling the occupants at the right detail to get the desired results. Then the next aspect is, how do we model occupancy or occupant behavior in general? We have different energy modeling tools, but do we have enough suite of simulation tools to model those occupant behavior or occupancy? So we have this suite of modeling and simulation tools that we've developed at the Berkeley Lab for the past more than a decade. And while some of them are specifically for occupancy, the others are broader for occupant behavior. For example, this driver needs action systems. This is just an ontology that represents occupant behavior. And then this ontology paves way for an OBXML schema, which is a standardized XML schema similar to what we have in the BIM for GBXML. And it is used to represent occupant models. And these occupant models could be anything ranging from occupancy models to window opening models to thermostat behavior, anything. And then the fourth one, the occupancy simulator, is specifically an occupancy related tool which is focused on office occupant behavior, office occupancy modeling, where we have this web-based app. You can go to occupancysimulator.lbl.gov and then input some of the parameters that you want for your office building, and it would generate you a realistic occupant schedule using stochastic Markov chain modeling that you could feed to your Energy Plus or other engine building energy model. And then there are also broader models like buildings.occupants, which is a Modelica package, and an OpenStudio gem, which is occupant variability, which has some parts of occupancy, but broader occupant behavior. And this is just a snapshot of what you could expect in the occupancy simulator, which is hosted at the LBL website. It has a Markov chain process and can give you zone level randomized occupancy for office buildings. Puts that you feed into the model. And this has been actually used for a variety of cases within the building performance simulation community. It's been used also by the PNNL Lighting Group, DOE's Hardware in the Loop projects, ARPA-E sensor projects, and obviously the Annex 79 community. So in summary, I would say that no occupancy model or even occupant behavior model is actually perfect. And real-world occupancy patterns are inherently complex and variable, but we have to make sure that our model presents the most realistic or the most accurate occupant assumptions that match our objective or intended purpose. And also this selection of this level of detail is also influenced heavily by what kind of data is available, or what are the computational resources or time or effort that is needed or available for the model development. And lastly, I'd say that we should follow a parsimonious modeling approach so that we can find a compromise between the data available, different levels of detail, and the computational time, so as to select the most relevant and adequate occupant or occupancy modeling detail. This also requires a lot of judgment, and particularly for new energy modelers or who are not as experienced, they might find it difficult to navigate to what should be the judgment. I would like to navigate to the ASHRAE Standard 209, which also has a similar level of detail appendix in the recent code cycle for broader modeling. And that could be also a good resource to start with. And yeah, I think this is all I have. Thank you.
Great, thank you so much. Does anybody have any questions, comments? That can include other presenters too.
I have a question. Is the intent to plug in similar weekly occupancy schedules, how we traditionally use with the 90.1 schedules, or is it to generate more annualized schedules? Airports kind of get busy and less busy as the season goes. Schools are the same. Thoughts on that?
Yeah, I think that's a really good point. I would say, again, it would depend on what's your intent. If you are looking at sizing a HVAC system for an airport, maybe you should look at seasonal variation to make sure that you're not undersizing or oversizing. However, if your use case is more related to the annual EY or something very higher level, then it would be okay to use more annualized occupancy schedules.
And I guess a follow-up is, the occupancy simulator, is there any intent to bring in different building typologies into that scheme?
Yeah, unfortunately, no, because we've tried that for probably the past 4 or 5 years, but we do not have any active funding or any active project that could extend it. But we also have we've also tried in-house Python codes for simple residential occupancy simulator. And if you are interested, I can definitely share some of those.
Thank you.
Okay.
Thank you so much. Appreciate the presentation. We're getting a good too. So yeah, so we'll move on to our third presentation, but stay tuned to the end because maybe someone else will have a question that links all three presentations. So Yeonjin, do you want to start sharing your screen and I'll do your bio? Great. So Yeonjin Yang is a second-year PhD student in the Department of Mechanical and Aerospace Engineering at Syracuse University, where she conducts research under the supervision of Dr. Bing Dong in the Built Environment Science and Technology Laboratory. Her research focuses on urban scale occupancy behavior, HVAC system control, and human mobility modeling. So looking forward to hearing your presentation. We'll hand it over to you.
Thanks for the introduction. So today I'm going to present my recent work about how to develop a fit-for-purpose framework for the urban occupancy modeling. And here comes like the big picture. Everyone knows that about like urban scale spends a lot of global energy, and buildings alone contributes to 1/3 of all CO2 emissions. By 2015, about 17% of the world's population will live in cities. This urbanization's challenges creates an urgent need for accurate urban building energy modelings. However, there's one major uncertainty from like the human occupant behaviors. So here's the challenges we face. Like researchers, we have like access to lower data source and cutting edge method, and we can produce very high accuracy results for the urban occupancy modelings. But meanwhile, for this, like the principals, like operators and planners work with very limited data and very limited budgets and maybe yesterday deadline, but they just need to some useful results for their specific purpose. So this gap between the researchers and the practitioners inspired our central like the questions: how do we create a systematic framework for fit-for-purpose model selections, and how can we select different data source modeling methods to do that? So here comes our framework. This framework is meaning-based, built on the two meaning like concepts. First one is, as Jeetika mentioned, it's a level of detail concept, and second one is like the space-based and the performance-based. First one, this level of details has been introduced, right? It's introduced by the Jeetika to the occupancy behavior fields. It can show different representations of objects at various resolutions. And the second one is to show the space-based and personal-based to distinguish the modeling strategies for different building occupancy modelings. And here comes our three core concepts for our framework. First is the representations, which means what units does each model represent, like from the average buildings, groups of buildings, individual buildings, to like the groups of occupants and individual occupants. And the second one is the heterogeneity. It's like the variation in occupant kinematics. It's maybe the occupancy can have the similar behaviors or diverse behaviors. And the last one is about like the modeling formulations. It's like it's deterministic fixed schedules or probabilistic statistical models. And according to this, we create our framework levels to 6 different levels. The space-based scale is mainly focused on like the building. It's space-based. It's like we generate the schedules from the building side, like standard deterministic schedules from some standards, and S1 means deterministic schedule derived from layers, like the first presenter did that. And like S2 is like probabilistic modeling across building groups. S2 is probabilistic modeling for individual buildings. And here comes the personal-based schedules. It's meaning from like human mobility. Data is generated from the perspective of the persons. Like we just models different like the human behaviors from the person side. And we can easily do the mapping, like we can easily mapping the data source, some data source and modeling methods according to our definitions. Like we can we have the individual level data, and it's surely for the individual level of details. We can have the building level data. It's surely for the space-based, like the LOD. But here comes like the big question is like when we really use it, the same data source, but it can have different level of details. The actual LOD depends really on like the data coverage and portioning methods. Like even we have the GPS data, for example, we just coverage about 20% populations, but it has limited like the representation list. So it's just can be shown in the LODP 0. But if we have all like the GPS data which can coverage all the populations, it can only be shown like the LODP 1. So LOD level is not just like the data type. It should be data type, coverage, and model method. The combination of this both. So how can we mapping the different application scenarios to the LODs? Because like for the resource constraints and implements trade-off and dynamic mappings, we have different choice for different like the application scenarios. We have to find a way to map this one. So we have the choose stage, like the application scenarios mappings. First stage is just like the literature based. We read a lot of papers and find out how people can use the different building occupancy modeling method in different applications. It's a very raw mapping. We can see that for urban planning, we can use S0 or S1, district energy system design or building performance benchmarking, like energy storage, renewable iterations, building level optimizations. Each of them can use many of the LOD levels, but we want to quantify it. We want to show something real. So we design a case study to validate our framework. We select a Phoenix neighborhood with about 800 buildings. Like it includes like the residential buildings, office buildings, stores, restaurants, clinics, and the churches. This diversity let us test the framework across the building types. And our method have 6 steps. The first step is to generate the GPS data which can coverage all the populations. Because we only have the GPS data, which is 1 month hourly stay points, contains about 2,000 users in this research area. It just contains like 20% populations. So we want to use this data to generate a sum like the ground truth data for this area. So we use the LSTMW to do that. And we also, after that, we use the generated real data to do the sampling to get the 2% survey data. And after that, we just get the human mobility data. It's human-based. We just know when the people will arrive somewhere, maybe they'll live somewhere. So we use the spatial joints to transfer the human mobility data, to transfer their movements to the building occupancy schedules. And the second part is to how we model it. We now have the different data types, right? We want to use it to do the modeling. So we use just one method is like the inhomogeneous Markov chain models, but for different data, like for human mobility data, we use it to calculate the transition possibilities between different locations. And for the building occupancies, we use it to calculate the probability between like the building occupancy ratios. So here, by this, we can generate like 6 LOD schedules versions for different type of LODs. And as last, we use the different 6 types of the generated building occupancy schedules to put into the 800 building energy plus models in this area. We change the lighting equipment schedules and we change occupancy schedules and also the fresh air rates accordingly to see the final results. And we use different, here's what we use to do like the evaluate the model performance. For the GAU model, we typically use the matrix like the KL divergence and FID to show the distributions of the generated data and the real data. And here is another is about the key performance indicators for different UBM applications. Like for district energy planning, we use total energy use. For the district energy system design, we use the peak energy use. And the building performance benchmarking, we use the energy distribution like the energy distribution, and we also use the KL statistics to compare the distributions. And also the energy storage renewable and the integration, we use the load durations and the building level optimizations. We use hourly patterns to see the difference. And here comes the results, because we want our generated data, like the real data, will really cover and represent the real, the whole population in this area, the real, like the mobility and something. So we use it to show that, and we can see that our GAU model performs well. So it's reliable and convincing to use it as our ground truth to continue our comparisons. And here we can show the different generated schedules for different LODs. And this one is the residential buildings one, and this one is the office building generated schedules for different LODs. And here comes the most important part is if we put the different generated occupancy schedules into the same energy models and change them, how comes like the UBM simulation results can be different? The first one, you can see that if we compare the total energy use, we can see the S0 can overestimate the residential buildings, but varied widely for office, and higher LODs constantly performs better. But we don't. If we want to just meet the requirements, maybe we can just choose like the S2 or S1 for different types of buildings. And also for like the peak energy use, we can see that S1 and S2 can show not the best, but the best choice, because it meets the requirements and also with the lower computation costs. And also comes to the energy distributions, we can see that S3 and the person-based person-based models like P1, P2 can best capture the variations across different buildings. And the load durations, we can see that for the of storage applications, and S1 have more than 20% error for residentials, whereas S2 just achieved under 4%. So it's better to choose the S2 is enough for these applications. And here comes the energy hourly patterns. We can also see that if we want to do that, S3 is good enough. And we can or see that the P0 or P1 level can meet all the requirements, but it's too high level. We don't need to do that if we just want to use it into the UBM. It's better to use them maybe in some infection risk or transportation, something like that. But if you want to just use it into the UBM, maybe choose the occupancy modeling from their S0 to the S3 is good enough. And here's the conclusions, like we first established the framework to for the urban occupancy modelings, and we also mapping the data source method and applications to different level of details, and we also quantify it and give some practical guidelines. But here's a lot of limitations because we don't quantify the data acquisition challenges and the computational cost, and also this case study is just focus on one area in the Phoenix, Arizona, so we may need diverse urban concepts to do more case studies. And also, we all know that the relationship between occupancy and the building operations is not very simple. There's more people, so there will be a higher cooling load, maybe something like that, because maybe sometimes occupancy didn't influence the building operations. So here's a big problem that. And also, so for these points, we just focus on the maximum impacts from the occupancy. So it's maybe, I think it's just the maximum impact. It can't to represent a real influence to the real buildings. So maybe later we'll do more work to reduce the gap between it. And that's all. Thanks. And any questions?
Great. Thank you so much for the presentation. Yes, any questions?
So I have one question. If I'm modeling like a college campus, well, that's a bad example, maybe like a military base where there's a known population, it's easier. But in the case of a city where some people might live in one of the buildings but work outside of the study area, or work out, the reverse, like work there but not live there. And I'm wondering how do we deal with that boundary condition of people who might leave the study area?
Yes, that's a good question. When we to process the data, we will give each of the the location a label. Like if he's out of this area, the label is 0. So when we generate the data, so it's just it's 0. It's just a unique label for the living people, something like that.
Okay, thanks. That's great.
Any other questions?
I have actually one question. So I understand this is more focused on the urban level, so the accuracy might be not really focused on one building type, but just curious about the technologies of GPS. So how accurately detects the GPS not only for the presence of the people but also for the actual exact location inside the building? Is it possible to detect those detail or granularity of the GPS within the building? Like if we have some, we want to utilize this method to apply for one building type, maybe we may need to apply for different occupancies for different space types. So do you think, is it feasible to utilize this GPS technology, detection of GPS technology to model in just one specific building with a little bit higher granularity?
Oh, yeah, that's a good question. That's what's we also like to meet the problems when we do the research. It's why we choose this area, because for this area, it's doesn't like New York City. It's have high-rise buildings. So for this area, it's just one building, just have one layer or something like that. So it's very easily for us to locate a person in these buildings, and we also use our previous research to extract the state points and we allocate the people to this building. So it may cause some error, but we cannot find a better way to deal with this data. Yeah.
Thank you.
You have a question, David?
Oh, well, what I was gonna say, if we could switch to kind of the more
Yeah.
informal
Yeah.
section now, and I can turn off the recording, that way people can speak more freely and
Yeah. Yeah, let's do that. I was thinking the same thing. Perfect. Okay, I'm gonna stop recording.